I mean, it's the perfect number.
Yes, this is the most important number. The whole number system, the unique number.
Just imagine something to zeros and just say this. You see the number system of the application. They don't have the zero.
Which number system?
Aspect.
Okay.
Okay. So they don't have a place to hold them. Like that. So they so if you think about Roman now do multiplication using Roman numbers. Easy to easier to use. That's why you even do. Right.
Esteban, can you do problem 1?
Should we submit?
Yeah.
All of the parts?
Let's see how it goes. Maybe not.
Huh?
Let's see how it goes. Maybe just the first.
What happened to the random number generator?
It wasn't random enough. No, I realize some of you don't have enough
Exposure.
yeah. So I need to adjust it.
Okay. Problem number 1 states it divides into 3 parts. And the first part I think is optional.
Okay, we can do part B.
Well,
If you haven't done part A,
I
just
did it,
do
but
part B.
I'm not sure if what I did is okay.
When you did. Alright, let's do part B. Then later, if you have time, we can go to the optional.
The part B states calculate the small angle scattering. The scattering angle in lowest order in 1 over b. B is the impact of parameter for a non-relativistic and ultra-relativistic particle. And in particular, calculate light deviation by the sun for a light ray just grazing the surface of the sun with a solar mass and the radius, and give your answer in Archimedes. So that's the B part. So the problem asks to us about this. And we need to compute the angle of the scattering of one particle due to one mass m. So it's supposed that the particle do something like this, and we need to compute this angle. Okay.
Maybe you can also show what is B in the,
Ah, yeah.
in here.
According to this, B is the impact of parameter, which is the distance, and it's defined as the distance at which the particle starts to bending. And I suppose that.
But the definition is really that if you turn off the interaction, so if it just moves in the straight line, B would be the closest distance.
Okay. The closest distance to the non-interacting path.
Yeah.
Or something like order 0 or. Okay. So we can start using the geodesic of, well, this is a particle in space-time, so it satisfies the geodesic equation. So, and we can use the linearized version in such a way that, for example, as we saw in class, where the metric is given by
H alpha will.
yes. So, okay, we need to introduce this in order to get a differential equation. Okay, and then we can, well, cancel this part. Because we have to get a differential equation over, we have to put the whole expansion of everything step by step.
I don't know.
Because we get from here to differential equation.
But maybe you should tell us what you are how you are trying to solve the problem at the end. Like what is theta? How are you going to find theta?
Okay, I need to. Well, I know that the tangent of theta can be computed as the change of momenta in y over x. So this angle of first order is like goes this way. So I need to compute the momenta when the force has already acted
Uh-huh.
over the x component.
So to what order you are going to calculate P? To what order in H you are going to calculate Py?
First order.
And what are Px?
Order 0.
Okay, so what is Px?
Px is the well, this is the final. But I should get to this doing this differential equation integrated because
but you said you want Px to 0th order. So for
yes,
that you don't need an equation.
Because that the velocity of the particle.
No, I'm just saying what is Px to 0th order?
Is the velocity of the particle in the non-perturbed trajectory.
Isn't P momentum?
Hmm?
Isn't P momentum?
Yes.
Okay, so what is momentum?
But
Given the velocity, what is the momentum? So that's the non-relativistic.
it's non-relativistic.
If you want to do it for life, okay.
It should compute.
Okay, so we need Py. We don't need P. We don't really need Px. We really care about the y component of that equation.
Yes, but we are considering a non-relativistic and ultra-relativistic particle. So
Right, but in both cases we only need the y component of that equation. So let's just write the y component of that equation.
From here, or can I put the whole the result of expanding this?
Well, I don't think you need to expand many things if you just care about the y component of that equation. Let's do non-relativistic first to warm up. So let's just look at the y component of the equation in the non-relativistic case.
The free index.
So I guess you are using the other signature when the spatial component of Minkowski metric are plus 1.
But yes,
It's minus 1, 1, 1, 1.
but
If you are
it has to
looking at
be
the
the same, right? It has to be the same, no matter how signature do I choose.
well, except that the differential H here changes.
Okay.
Because when you change the signature, it's like multiplying metric by minus.
So
Okay, so let's focus on the non-relativistic case
remember
first.
how I did this. The non-relativistic limit.
Yeah, so what would be, can we make some approximation in this equation?
In that case, I can interchange the proper time for particle and non-relativistic limit.
Okay, so that falls on the zeroth order of this equation. But it's correct. Yeah.
Okay.
Yeah.
So,
What else?
in this case, I have to consider for the particle that the energy is all of the rest mass in the definition of this object that we did in class. That up to all other orders. This order. Then
So can we simplify this equation using the non-relativistic approximation, Newtonian approximation?
because this I will get from here spatial components of velocity when I expand this contraction. So I have from the last exercise, the part A, that HAV looks like is diagonal.
Yeah, let's wait a bit before plugging in the actual values for H.
Okay.
Let's first simplify the equation as much as we can, and then we can consider what is H. Because we know that H is small, and we are in the non-relativistic limit. So with this information, we should be able to find the simple equation of motion, and then we can plug in what is H. But first, let's just keep H as some unknown known function, but as H. So what does this mean? Does it mean that you do not take the time derivative of dy dt? So already here, can we make some extra simplification? Yes. So dy dt can act either on dy by dt or on H22, right?
Yeah, because it's not depend on time. So, and suppose that the H is small, right? So I can neglect this and get directly the derivative of y, right?
What are the right hand side?
In this case, I have to use the fact that another person is diagonal.
Okay.
And I will write the 0. And this object appears. then, but I know this object from the non-relativistic estimation, that should be 1. And this is the no components of velocity that well, because ij is diagonal, so this is a velocity squared.
Sorry, what does HIJ mean? Like you have free in this IJ. We cannot have free in this.
If I want to, we can write something like this.
Okay, and the non-relativistic limit, what is? Can we say something about that second term?
Well, because this non-relativistic limit, I can take the velocity. Well,
what's the definition of non-relativistic?
That I have be much less than 0 or than 1.
Okay. So can we
This
say
is a
something?
small, which means that even I can collect it. But I know the H00 component from the last exercise.
Let's call it RG. It's R in sub G, not G.
What?
It's
It's
RG means R gravitational.
yes. And R is defined as the distance of a particle but because I'm doing it but because I have to evaluate this at 0 order, the non-perturbated trajectory, which means that I get from here. Instead of function of y, I will get this object.
I cannot. I don't understand. Is it a scalar or a vector?
No, it has to be a scalar, sorry.
So what is the y derivative of this?
We write here for clarity. So I have that. And I have the differential equation over G, or y, sorry. I think I have to keep the y dependence because I'm deriving over, so I cannot, because I have a derivative term here, cannot use this one directly, I guess. So let's keep the y depends.
Why do you have two RGs? And there's RG. So you took the derivative, or what? What did you do?
I took the derivative over y. Because it's like a force that particle field.
Uh-huh.
I because I'm derivating this, it goes down to 1/2, and subtracting 1, 3/2. But because I'm pulling down 1/2, and I'm taking the derivative of this, I will get 2y.
There's another up front. There's another 1/2.
1/2 comes from the definition of the
Sorry.
And yes, because minus sign. So I have a differential equation over y. So something that I can integrate. Then integrate this. Evaluate this, the zero at zero order because I'm doing at zero order this expansion. I think I should evaluate this over the parameter for this quantity, and even I can change because the velocity is almost over x-axis in order to change the variables. We'll be able to perform the total change of momentum. Then I have to do that integral, sorry, which is
But if it is in your notes, you can use it. You don't have to do the integral process.
b squared, I think. No, but pi over So I have some numerical factors. They asked me about them. Calculate, so let's keep it there.
And then there is a pi there.
It's like arc tangents.
Also, there was a factor 1/2 that got lost in translate.
From here,
Yeah.
everything is correct of the sign.
Okay. I think this is the correct one. No, without 2. You get a 2 from the interior. Yeah, I think that's good. So what would be the angle?
So the angle.
By the way, can you restore factors of C in this result?
It's the factor C.
Just by looking at your final answer. Where RG is called RG because it's something of dimensional length. So you don't need to think about dimensional RG.
So this has to be, should have dimension of length over time. So I have length here, length here.
Okay, what is the angle, theta?
Then the angle. Have to put this inside. Let me check again. This is dimensionless.
Yeah, it's correct. Thank you.
Okay.
Julian, can you do it the relativistic case?
again, the zeroth order trajectory is x equal t, and y equal b. So the terms with y dot go away. So this is not there. This is just 1. And this one is 0.
Wait, dot is the state
Till proper time.
and but then what is t dot then?
We have this is 1 over gamma naught.
Mm-hmm.
And then
Well, 1 over gamma. Remember what is for velocity? Do you remember what is for velocity?
Just for a relativistic particle, you would have this is 1. It's moving in x.
In general, imagine some particle moves with velocity v.
Yes.
What would be its for velocity? U mu. For something that moves with velocity v. Okay. Now, what is the definition of for velocity in terms of derivatives of the coordinate? Okay, so now
it's gamma.
Okay. So what is t dot then?
Gamma squared.
T dot is gamma square
T dot squared.
and x dot.
Sorry?
And what is x dot?
Gamma times bx squared. Okay, so there are gamma squared factors in both.
Right.
Setting
One other thing. Or maybe you are going. Maybe we should continue. I ask you later. Necessary.
we can just plug y equal to 0.
But do we need to keep this RG over R?
Sorry, I know, because it's since the field is weak, only the first term is important. Yeah.
Yeah.
So this is just this thing, and the 1/2 goes away, and this is just RG minus. That is y dot dot. And we can do the same thing again for so we need is y data at least. Yes, no.
Well, how do you get this?
It's from instead of using the momentum, just the velocity, no? And just just use the x component of the velocity and the y component, and this is just it should be the acceleration here, and then just multiply point out by the time interval.
I'm just confused about dimension. So what you are writing is something of dimension, something with dimensional length. While theta should be dimensional length.
Am I missing?
Where double dot?
I'm using.
I also didn't understand it. Can you repeat your definition of theta in terms of velocity in this geometric picture?
So it would be delta py over px. And then it's just cancelling them out. Delta in Vy would be x. And then this would be
Is it only the mass if it is relativistic?
you substitute. For px it would be the energy. Okay. And this would be delta gamma.
But also we can again relate it to the force velocity, right? So there is we have a relation between force momentum and force velocity.
Yes.
So can we write it? Can you write it in terms of the component of force velocity, like p by? What would be p by as a function in terms of the force velocity?
I'm not sure what you mean. It's no.
Okay.
Py.
Yeah. And we know that u mu is dx mu by deta.
Yes.
So what would be p by? It will be m times dy by deta.
Yes.
Okay, so if we know dy by deta, at the end we are done, because we know that at the beginning dy by deta is 0. So just for clarity, can you put an index of dy by deta final? Because it's then okay.
Okay, yes. Now we use the y dot is so integral y dot deta just be and then here we could just put the approximate these values to get the answer. So we can just take R equal to B and
Okay.
delta T again to be delta X.
Well, we should, we know what is dx by deta, so we can change the variable.
I'll just I was just plugging in the not to do the integral explicitly. There's a bunch of square.
Okay.
This is setting C equal to 1. It's just this.
And no, wait. So deta is what is, you can write it as dx divided by dx by deta.
Yes.
In general. So let's remember what is dx by deta. So maybe we can again write for velocity.
Gamma E, gamma
Mhm.
Cx.
Right, and what is Vx?
And
In the ultra relativistic limit is almost 1.
yes.
Okay. And you are calculating the absolute value of dy by
Yes.
deta.
Yes.
So if we really wanted dy by deta, it would be minus this.
Yes.
And this is the same integral as we had before. So we know it just gives us a factor of 2. Up to, I mean, there is some dimensional analysis to be done, but the integral just gives us 2.
What's the result again?
Well, if you fix the dimensions, I fix the dependence on RG and B, I'll tell you the numerical coefficient. But can you just guess what would be the result, or not guess? Say what would be what would be the parametric dependence on RG and B and gamma for that integral?
Taking this equal to B and this to be B would be 1 over B times, or G times gamma times some numerical factor.
Okay, that numerical factor is 2.
Okay. Above or below?
No, above is 2. No, we are not done yet. The problem doesn't tell us E.
This is gamma M. So this
Okay.
cancels this thing above it. This 2 over G over B.
Yes, it's correct. So can you do one exercise now? Let's take the non-relativistic result, and so is it still there? No, it's not. The non-relativistic angle was RG over B V squared. So we can do the following exercise. We can set V to 1 in the non-relativistic result and compare it with what we got here.
What was the other one?
It was, so let's write now that, yeah. So this is RG over B V squared. we set v to 1 in the non-relativistic result, we get 1/2 of the actual answer.
Yes.
That's as the use back. I mean, this is the thing that Ed Langton was trying to check in 1920 or 1921. Yeah. But I think at the end of the day, they didn't have enough precision to determine that factor of 2 difference. So he was pro GR. So he claimed that his measurement is consistent with GR, but I think it was consistent with both. Okay, thank you. Alejandro? Oh, not here anymore. Ahmed? No? Not even Esther? Oh, no, sorry, you are not Ahmed.
I'm Ahmed.
You are Ahmed.
Yes, but
But
I can do it.
you cannot. Okay. Are you good, sir? You want to do the next part?
The number 2. Or
No, number 1, part C. Just estimate, you don't need to calculate.
yeah, okay. Sorry. Okay. I hope I don't need my notes. Can I erase something?
Yes. Yeah, please erase everything.
Okay, so we have okay. The formula in for spin 2 goes like something like this. Actually, correct me if I'm wrong. So we need to calculate this. To estimate, we need to give some number for this. This is this thing. And okay, if we're
No, sorry, it depends on mass too.
yeah, sorry. Yeah, okay. So if we're gonna give some estimate of this, we better take the derivatives. This should go, okay, if we're gonna estimate, do not calculate, this should have, if we use like the Newton expansion or the general, if we just use Leibniz rules, we will get things like this. One term with this, and another term with this, and the exchanges of these terms. This will have a 3. So we already know this from the previous exercise, and this should go because okay, let's put actually. So
y. Okay. They should all go like Newton. So that's 2. I'm not doing that. And okay, this is the first. Yeah, let's. X dot is not moving. No, it is moving in X. So that's B to 0 order. And Y0 to 0 order is moving in this direction. So we take it to be 0. And to calculate this, we can differentiate this expression and then substitute the non-perturbed.
Can I suggest that you just consider the second term?
Which this one?
Yeah. And
Okay.
assume that the first term is not much larger than the second one.
Yeah, it should be.
It's a correct assumption.
About the same or less. So okay, so then this thing we will have let's say Q triple dot XX. So then we have so if we're only considering this, we have X double dot X, and that's so we have this here, right? So this is 2, and this goes like this. And if we consider that the the area along X, that the interaction is important, is of order V. We can also use B for X, and then I need this one. So this is B. Am I right? So this is.
Well, I think there are many factors of 2 and 3 that are not there, so maybe you can also drop to that final one.
Yeah, this one, right? Yeah, probably. Yeah, they have because there are 2 factors. It will actually be a 4, because okay, it will be 4, but so now y. This will be so y is the same thing. And well, we have y dot is 0, so it's 0. To first, to first ordering this. What else? And we also have the cross term. So this will go like this, and the other one is 0. The other cross term. So this will go. This is.
Well, I'm afraid this is too precise to be correct, because doesn't QYY contain a term which is just from subtracting the trace? Doesn't it contain something that is actually non-zero?
This thing. You mean this thing?
Yeah, so that will also exist in the QY.
Oh no, I can write it like this.
Okay.
It's the same thing. And I will also have.
I'm just saying that if you look at the by component, because so I and J are gonna be by, say.
Yeah, this is this, and You say there's there's gonna be another one that is the same order as this one.
Uh-huh.
Yes.
So
Yes,
at
you're
the
right.
end of the day, all of them are at this without putting the numerical factors, all of them are of the same order. Maybe actually some of them cancel to zero, but not all of them.
Yes, you're right. So this other factor. So yeah, all of them, at least those terms are of this order. So now we can the square of this thing is gonna be like the square of those things. So that's and the mass. Huh? So now we can plug this in. So L is gonna be G. Yeah, 45. Gonna drop. And the energy, if we integrate over time, the power. The important time should also be about the time of the interaction, where the interaction is important. So the time scale will be like about the time the particle goes across the interaction area. So that's should be this order. Yes. So then this thing goes. So then this thing goes like. Which is of this order.
Yes. Okay. Thank you. So what is the answer to problem 2? Who says yes? Raise hands.
Absolutely yes, exactly yes.
I know you do or you don't.
What do you mean?
Practically yes, or exactly, mathematically exactly. Yes.
Detectable?
Well, if it is a conditional, I don't know. I mean, so it's
Yes.
yeah, answer. Who says yes? So no one says no. But you have some disclaimers. Can you say what is your disclaimer?
Essentially no.
Why? No, but why is no?
Essentially no.
But why?
The power loss will be, the energy radiated will be negligible. Will be minuscule, like inconceivably small.
When you talk about minuscule energies, should you take something into account? The fact that the word is not classical but quantum. So if you take that into account, is it still minuscule or 0?
Oh, okay. What is the Planck energy? Is it 10 to the what?
38.
What is the Planck constant? Are you asking what is the Planck constant?
Minus 34, right? Minus 34.
Minus 34?
Yes. 10 to the power minus 34.
So you can ask how long it takes to, you can estimate the power, right, when you move your hand using the same formula.
Yeah.
So you get some number, some minuscule value for the power. Then you can ask how long does it take for the energy to become the energy of a single quantum with that frequency, right? So you can ask how long does it take for the energy to for the energy, the emitted energy to be a order of the energy for a single quantum. Right?
Yeah.
So then you can calculate this delta t, which is h bar omega over L, and then that is some time scale. If it is longer than something, then most likely you do not emit gravitationally. This time happens to be, I think, happens to be a order of the age of the universe. 10 to the 13 year. So.
With the frequency, characteristic of the cosmology is
Yeah. Say 1 second. 1 hertz.
What do you say that you don't emit?
Well, at the quantum level, the world is probabilistic. So if you keep moving your hand from the beginning of the universe until now, you will emit one gravity at some point. But if you move for any finite amount of time, the probability of emitting it is negligible.
So the answer is
probably not.
it can happen.
But I have a question. You were saying that day that it depends on the direction of the hand you move. Is that, how is that?
It depends on the direction of.
Yes. How you move your hand? I mean,
Well, this answer, no, it is very general. I didn't use
yes,
the
yes,
direction.
yes. But does it depend on the direction of the hand?
Well, the way you move your hand is going to change this cell by some order 1 factor, but not by order 10 to the 13. So probably you can move your hand in such a way that it's 0.
Okay.
And maybe you can move your hand in such a way that it's a bit larger. Like there's some range of possibilities. Okay. Problem 4. Ahmed, can you do problem 4? Okay.
Okay. So the question says basically consider a burst of gravitational waves of the form HYY minus HZZ, which is equal A cosine omega t minus X shining on LIGO mirrors perfectly free masses in y direction, initially separated by delta y equals L, which is much smaller than C over omega. Calculate the time it takes, measured by the clock attached to one of the mirrors, for the laser light to go to the other mirror and come back. So we have two mirrors on the y axis. A laser shines here and comes back, and we want to calculate the total time of this trip in this gravitational field. So we will have G mu, which is eta mu plus H mu, which is more or less minus 1 plus 1 plus H plus H. Yeah, that's zeros. This way. So by doing space-time diagram, this is the y direction, this is t, this is y equals 0, and this is y equals L. Okay. So we shine light photon from here. So we need to calculate 2 times T1 and T2.
So these lines of y equal to 0 and y equals to L are the locations of the
two
mirrors.
Yes, of the mirrors. And then this traceless transverse gauges, they don't change.
Okay, so the non-relativistic masses do not move along y.
Yes.
And that's the result of the geodesic equation, right?
Mm-hmm.
Because the non-relativistic masses only care about 0 component of H.
So we have here, okay, what was confusing for me, this was this X, just like that. Okay, because I'll use the d squared, which is equal to G mu dx mu dx mu, which is for the photon essentially equals to 0. So I have minus c squared d2 squared plus 1 plus h d y squared, which is equal to 0. So I can estimate or I can calculate the velocity of the photon function t
t, which would be equal to square root of dy dt by half. Should be c over 1 plus h t whole to the power half. Then I can use this to calculate the time for the trip t1 and t2. Just say that t1 is integral from 0 to L dy over v t prime, or t prime is the retarded time. I can just do this here. From 0 to L, this would be.
Sorry, can we do something before taking the inter? So what would be the time that it takes for the photon to go and come back if I turn off the gravitation? Yeah.
Should be 12 over c.
But do you have the numerical value?
Numerical value of 2L over c, yes, it will be 2.67 times 10 power negative 5 seconds.
Okay. How does it compare with the frequency of the gravitational wave? We know omega, right?
We know omega, yes, omega is 100.
Okay.
It's 100.
So within one travel time, the phase of the gravitational field doesn't change much, right?
Yes.
So how does what is the phase change? It's just omega t, right?
Yes, it will be omega t. For the gravitational field, right? So it wouldn't change that much of it. And this holds true.
Okay. So therefore we can assume h to be constant.
Yes.
During the trip.
Okay. I didn't assume it to be constant, and I had a terrible calculation. Okay. So we can assume it to be constant. All of this is constant. That's fine. So we have this dy over v, which is v is this is c, and this is 1 plus h to our half, which is integral from 0 to L dy over c, 1 plus the amplitude A is very, very small, so we can just d half h t bar. So that would be, this is constant, this is here, so we will see 1 plus half h over t bar over c integral from 0 to L dy, which is just L.
So if it goes back and forth, it would be just 2L, right?
Yes, it would be times 2. However, if it wasn't constant, this integration would indeed terrible stuff.
Why did you say that the v is not 1? It should be 1. Speed of light is always 1.
Well, what is the meaning of v? I can just rescale y to v. At the moment you talk about metric, then no, the speed of light is not 1 anymore, because the coordinates that you use are arbitrary. We just divide dt.
Okay, yes. Okay. Yeah, if you put it in y, then.
But what is important is that in this coordinate system, the mirrors do not change. That's why we are talking, That's why we are interested in dy dt, because the mirrors are located at y equal to 0 and y equals L, even when you shine the gravitational wave. So that is important. The fact that the mirrors do not change in this coordinate.
They are at the same point, but
So
the
this is
distance
the-
oscillates, right?
Sorry.
They are I mean, they will remain at 0 and L, but the distance in between can increase, decrease, but they
Mm-hmm.
oscillate, but they will remain the same, right?
Mm-hmm.
So this is the output. Which is T, that T is in the, not in the, that's in
Is
the
T?
output.
Oh, you can also ask what if we are measuring the time using the clocks that are attached to the mirror. So those are the word lines. So the time that we are interested in is the length of this word line at y equal to 0 between these 2 points. So there is a clock that lives in this word line, and that measures the time.
Yes, in the system of the mirror.
Right. Well, attached to one of these. So you can ask what is the length, what is the time that this clock measures. Right? That's the question that we need to ask.
Yes.
We send this to the other mirror, it bounces back, and the question is what time does this clock measure? Now, we can relate the time that this clock measures to the coordinates, like to the initial and final time. And the relation is
Okay, we will relate the time this, which is this T total, right? That we measured, right? We want to relate.
So that was the time, the coordinate time between these two events. You want to ask what is the time that a clock which lives on that word line measures?
Should be the same.
Yes, it is the same.
Yes, because it's
Because the clock, do you want to explain?
no, okay.
The clock, so we said that the clock's measure is theta tilde, right?
Yes.
And theta tilde is just the square root of minus the square root of g mu nu. Sorry, is the square root of minus g mu nu dx mu. Now we have a trajectory which is at constant y. It just moves in t direction. So this reduces to minus g00 dt squared. But g00 is just minus 1 for all gravitational. So this theta is just dt. And therefore this is also delta tau total.
Okay, but what I'm confused about, I will just plug in this formula for, I erased it, for h, which is a cosine omega t minus x, right?
Mm-hmm.
Here. So what is this t? I mean,
What is t?
yes, this t, I mean, this is the time of what
The time that you send the photon. I mean, we saw that the time it takes for the photon to go and come back is much shorter than the period of your gravitational waves.
Yes.
So what it means is that so you have this result. You can plug in the value. X is just some constant. You can set it to 0. So what you get is that delta t or delta tau is 2L over C times 1 plus 1/2 A cosine omega t. So what does it mean? It means that the time that I measure, I keep sending photons and they come back. I mean, I label the photons so I know which one is coming back. And I measure this delta tau as a function of t. So what I see is that this is 12 over c. And then what happens is that it's just going oscillating with frequency omega with a tiny amplitude. So this is some log. The important thing is that the time it takes for this to go and come back is much shorter than the time scale for this variation. So for any trip, you can assume that it's essentially constant. H is essentially constant during that trip, but it is slowly changing.
I was very confused with this problem. Does the light ray follow still a straight line in the curved background? Really, like maybe if omega is a bit.
A straight line. What do you mean by a straight line?
It's a geodesic line.
What is the definition of a straight line?
Okay, yeah. You follow the geodesic equation. Or maybe, yeah. That's the best definition here.
Yeah, well, if it's not interacting with anything else, then it should follow geodesic equation. If it's interacting with something else, then maybe not. But we don't have anything else present. But if you want to consider the gravitational field of the Earth, but then it would be the geodesical in that more general field.
So there is no deviation because of gravitational waves?
No deviation from geodesic equation, because that is exactly what takes into account the gravitational waves. If you had photons interacting with something else, and that something else was present, then you would deviate. So okay, let me give you an example. Maybe this helps. Thank you.
Because I plugged that into the geodesic equation and it was awful.
In what sense it was off?
The differential equations were hard to solve.
Really?
Oh, because I had the second derivative was proportional to cosine, so the variable is inside the cosine.
Because of that cosine.
Yeah, let's say I consider omega to be a bit larger. Not that constant.
Well, still, photon is a null particle, so this statement that this line element is 0 for photon is always true. This is like an integral of the motion. It follows from geodesic equations. It's like talking about energy conservation. So sometimes it's useful to use energy conservation, but it always follows from the dynamical equations. But it's already an integral of the motion, so sometimes it's useful to already look at those integral equations. So I can give you an example. If you have you remember we discussed the stillaton gravity, some scalar that couples to other degrees of freedom. Now you can assume that you have not a scalar gravity, but you have another scalar field in addition to the gravitational field, and that scalar field, say, couples to some particles, but not to all. Then, in that theory, those particles who are coupled to this scalar field, if you produce some background, some waves of those scalar fields, those particles do not move on geodesic equation, because there will be an extra force on them. Or if you have electromagnetic force, and you consider charged particle in electromagnetic field, those particles do not move on geodesic. But if the only thing that you have is gravity, then by definition, your particles move on geodesic. Okay, what are the last problem?
I have a question with this one.
Yes.
Yeah, I still don't fully get why doesn't the distance between the mirrors change?
Oh, the distance. Well, I didn't say the distance. You mean why is the trajectory of mirrors y equals constant? Well, that is the consequence of geodesic equation again. That's the only thing that we need to do. So in this problem we have a photon and then these two mirrors which are supposed to be free should be regarded as free massive particles which start from rest. So let's write the geodesic equation for the mirrors. Then this is basically what we did at the beginning. So we have y double dot equals 1/2. So we are assuming a small field, right? H is a small fertility. So we were getting y double dot equals 1/2 dy of H00 for a non-relativistic particle. Now, for the wave that we are considering, H00 is 0 in this coordinate system. That means that y double dot will be 0. Now, since they start from rest, then since y dot initially is 0, that means that y remains constant. Y dot 0 equals.
How would the distance look from infinity? One who's not on the field.
Oh. Well, that's a good question. You can, we should first, I think, come up with a protocol to measure. Say they send 2 photons. So we say that, how do we do? I guess we can ask them to send 2 photons or keep sending photons. And then see the arrival time of these 2 photons. Then it will change because of this calculation. By the time it takes for the photon to go from here to there is going to change in the presence of gravitational waves. And then from here to infinity it would be the same as before.
But then you're saying that from infinity you would see that the distance changes because of this calculation.
Yeah, but I mean, you should define the when you say from the what you see from the infinity, you should come up with a definition of how do you measure distance from infinity. So I'm saying if you measure it by sending photons, then yes, I think it's going to check. But here we are not. What we are doing is that we are saying we send the signal to go back and forth, and we measure the time that is measured by the clock that is sitting here. And that is also changing. Of course, you could choose a different coordinate system. You didn't have to use this coordinate system. You could choose a different one, and in that coordinate system, the particles would move. So the fact that they are sitting at fixed values of y is nothing very deep to be worried about. What is more physical is what is the answer to different measurements that they can do, like the time that it goes back, the photon goes back and forth, or what we are asking this next problem, that if what happens if I attach these two masses by some string, is the string going to resonate or not? Okay, so what is the answer to the final problem? Who says yes? It's going to resonate. 1, 2, 3, 4. And who says no? You.
I didn't do it.
Oh, you don't know. Can you explain why? Do you want to come and?
So in number 5, the meaning of a rigid ruler is basically saying that the space-like separation between the ends of the ruler is time independent. So it's given by L. So what we want is to calculate the space-like separation between the two mirrors. It's given by time. Sorry, it's H, Y, Y, dy. H, Y, Y is not a function of E or X. It's not a function of Y. So if we expand this.
Sorry, can you explain a bit more how you get that equation dl prime equals the square root of 1?
So we start from the definition of the invariant, the differential length, which is g mu dx nu. Now, if we want to look at the difference, the differential difference between between y and y plus dy, then this explicitly reduces to d squared.
Can I propose something?
Yeah.
So let's imagine that instead of two mirrors, I have many of them, or many little masses that sit in the interval between y equal to 0 to y equals So maybe we can draw them in this space-time diagram.
If we think of them as in the many mirrors, and we want to measure is uh, this is the space-like separation between the mirrors such that we measure it at equal times. In such case, for ds squared will then reduce to dyyy dy squared. It's just equivalent to dy squared. Now, in square root, find that space-like separation is basically y dy at that instant of time. So we then, since hyy a is 10 to the negative 20, we can expand it to first order. Yes.
So here the logic is that ds is something that the good ruler measures.
Yes.
In the same way that when we have a time-like trajectory, the tau tilde was the thing that the good clock measured.
1 plus half h y times dy. Now if we integrate it to L prime ds, and we integrate this thing, this is a function of t and x only. We find that then find that space-like separation actually, the difference between L prime and L, find that it oscillates
Set x to 0.
and then find that the L prime, which is the space-like separation measured by the good ruler, and L, which is the separation, which is, let's say, the length of the rigid ruler, with L prime, the space-like separation between the two mirrors, and L, the space-like separation of the rigid ruler, we see that it oscillates. It's a oscillatory function, which oscillates a frequency omega. Now, if we then attach a spring between the two mirrors, you then see the spring should oscillate 6. What the spring measures is actually the measure of this. What the spring measures, the spring measure is not the coordinate distance, but the space-like separation of the mirrors. So it should oscillate if it's if its constant, spring constant is km over m, k over m is equal to omega squared.
It always oscillates, but if it is close to omega squared, then it resonates.
Yes, it has a.
Okay. Thank you.
I have a question.
Yes.
When LIGO measures gravitational waves, they use interferometers.
Yes.
So they basically do interference of light being squared.
Yes.
But if the gravitational wave will stretch the wavelength of the photon, wouldn't it? It's a greater optical path, but it will also like change the length of the
When
maybe
you
it's
shall
like-
ask, it changes it.
Will it affect the measurement?
With respect to whom? So you are talking about the gravitational redshift or what?
Yes, in gravitation.
But remember, gravitational redshift was sensitive to H00.
Yes.
Basically, for the same reason that what the clock that sits on one of the mirrors that doesn't change, that measures the same coordinate time. For the same reason, the frequency of the photon shouldn't change either. If I send the photons using my clock, so I'm sitting on the mirror, and I use my clock to produce the photons.
Yeah.
Right, I fix the frequency so that the wave fronts are at fixed times compared to my clock. Then it should remain the same. Or in other words, the frequency of the photon measured by me it remains the same, it doesn't change.